I welcome you back from the coffee break. And we have a superbly interesting topic to talk about now. 2 years ago, ChatGPT proved AI wasn't distant future. And now quantum computing is having its time for this paradigm shift. And coming to tell you more about it is Vijoy Pandey from Cisco. Vijoy, come, the stage is yours. Welcome.
Thank you, Christina. So, human progress in science and technology is driven by paradigm shifts. We have all seen a few of these in our lifetimes, the last big one being the transformer moment or the ChatGPT moment that we are all well aware of. But I'm here to talk about another one that is going to happen pretty soon. But before I do that, let me get to one of my favorite quotes, and this is from Thomas Kuhn on scientific revolutions. And paraphrased, what this really talks about is all scientific progress is done in these step functions, which are these paradigm shifts. But it takes us, humanity, decades or even centuries sometimes to truly utilize the power of a paradigm shift. So let's start with an example which is pretty familiar to all of you. Few blocks from here, in 1865, Mendel laid out the foundational building blocks of genetic engineering. But it took us 150 years to get to truly utilizing it for the first time in genetic engineering through techniques such as CRISPR. And guess what? It's going to take us another few decades or even centuries to truly utilize genetic engineering to the fullest. Another such paradigm shift has been predicted by Richard Feynman in 1981 when he said, let's go to quantum computing, or computing using qubits, quantum bits, instead of classical bits to simulate really, really hard problems. Why? Because nature isn't classical. Nature is quantum. And if you try to simulate and solve problems in nature that are really, really hard to do, you will end up using exponential resources, whether it's time, storage, or compute, or all of the above. And you see that time and again when you try and see things like drug discovery, things like weather prediction, things like new material discovery, financial transactions and simulations, or even logistics and supply chain management. When you think about solving problems in these spaces, it takes exponential amount of time. For all the computer scientists out there, these are all NP hard problems. They're not easy to solve. And so we thought we would use quantum computing to solve some of these problems. But we've been working on quantum computing for quite some time now. So why do I feel that this paradigm shift is just about to happen? To get that feeling certified, I took a look at all of the breakthroughs that have happened in quantum computing over the past few decades. And that's what you see in the chart behind me. And what do you see? You see the breakthroughs picking up pace. They're getting exponentially more frequent. And that tells you that there is a step function waiting to happen. So what is that step function? What is the suspense that I'm going to talk about? So to truly solve some of those hard problems that I discussed earlier, material discovery, drug discovery, weather prediction, and so on, you need somewhere between 100,000 qubits to 1,000,000 qubits to solve for those problems. Each quantum processing unit at the cutting edge today from all of the manufacturers out there is roughly around 100 qubits. So there is a massive gap between what is real, 100 qubits, and what is required, about 100,000 qubits. How do you close that gap? One way to close that gap is to build bigger and bigger QPUs, go vertical. The roadmap for that, when you hear numbers like 10 years, 20 years, that's the roadmap for that vertical scale up. But there's another way. Knowing cloud computing and how we've done distributed computing, you can go horizontal. You can connect 100 or 1,000 of these 100 qubit computers through a quantum network and get to your 100,000 or 1,000,000 qubits. And that is possible today. But why stop there? The supercomputing architecture of the future is going to be a combination of quantum computing nodes with classical traditional computing nodes such as CPUs, GPUs, and DPUs, all of them connected through a singular network. And that is what we are doing at Cisco. So what we're doing is we are building the entire quantum networking stack towards building out a quantum internet, starting with a piece of hardware which is so crucial and critical for this network. We announced this back in May. This is a quantum entanglement source chip. Very simply put, it generates entangled photon pairs, pairs that actually go left or right or diagonal at the same time, at 200 million entangled pairs a second in that chip. And it does that at really low power, really low cost. So you can throw thousands of these in your environment. But most importantly, this chip operates at room temperature. So all of those cryo chambers that you see, you don't need that. It operates in this temperature. And it operates at telecom frequencies over existing fiber, which means you can use the quantum network alongside your classical communications that happen today on existing infrastructure which you don't have to rip and replace. So that's the power of this chip, but it does not work alone in solo. It needs a software stack. And this software stack we announced in October, about a month ago. It's got everything from simulation, emulation, as well as protocols, control plane, and some really neat applications. One of the applications is a network-aware quantum compiler that allows you to take a quantum algorithm, a workload, and distribute it over hundreds of thousands of these QPUs. That is critical to enable that goal of going horizontal. But there are two other use cases that we are really, really excited about. And these two use cases are valid for traditional classical computing today. The first set of use cases, we're calling that quantum sync. And that is enabling faster than light decision coordination between any two elements. They could be CPUs, GPUs, data centers, whatever. And that coordination is instantaneous because it's based on quantum entanglement and teleportation. It's not information traversal because then you're breaking the laws of physics. It's decision coordination. So there's some really interesting use cases like high frequency trading, where you need to coordinate decisions across data centers that are scattered across the globe, or clock synchronization for really large databases in cloud instances. There's another set of use cases that is based on quantum measurement, and we're calling that quantum alert. And this is for the paranoid. So if you really want to detect an intruder in your network, you can use quantum alert to provably guarantee you that there is an intruder or not inside your environment. And these classes of applications are valid today. You can run them today using a quantum network that we have built for today. So I like to say that classical computing has a physics problem. And some of those challenges that I talked about earlier is a physics problem. You can't go beyond that. You cannot go and coordinate decisions faster than the speed of light. You cannot tell if there is somebody in your network or in your data center, provably, without having quantum properties. Quantum computing has scaling challenges. You can only scale up, you cannot scale out or horizontal. And voila, quantum networking is the solution to both of them. So knowing this, I have a few questions for you, the audience. For founders and investors who are all here, what can you do? What are the new applications? What businesses, startups can you deliver, can you build, knowing that you can work around some of these physics challenges of classical computing? For enterprise leaders, the fact that we can now scale out, there is a quantum day or a Q day attack scenario that is actually faster than what you thought would be possible. So how can you use quantum itself to guarantee security against those kinds of attacks? And finally, for European leaders as a whole, thinking about that supercomputing architecture that I just talked about, how can you future-proof whatever you're building today for that architecture of tomorrow? All of this awesome work is actually happening at Outshift by Cisco. We are an internal incubator. I run that group. And we are looking at problems in the quantum internet and quantum computing space. We're also looking at problems in the agentic space through this vision of an internet of agents, where you have a lot of these agentic pieces of software that come together, collaborate in an open and interoperable manner to solve for a business need. So if you want to learn a lot more about this, go to outshift.com or connect with us at Outshift by Cisco. Thank you.